Hello everyone, guten Morgen zusammen. My name is Julia Niesner. I'm a PhD student at the Department of Cyber-Physical Systems at the University of Siegen. Together with my co-author and PhD supervisor, Thomas Ludwig, we wrote the paper on Design of a Knowledge-Based Recommender System for Recipes from an End-User Perspective. Let's get into some details. With a growing number of products in several areas, the problem of quickly finding good alternatives gets increasingly important. Recommender systems, as used for example by Netflix, Amazon or Facebook, support the user by recommending individual items that might serve the user's needs. By supporting the search process of the user, his or her satisfaction and loyalty may be increased. However, even if the performances of recommending items based on past user ratings already has delivered quite good results, the field of recommending items without past data is still a smaller research area but equally important. Also in the cooking area, recommender systems might support the consumer by finding good recipe alternatives in everyday increasing recipe databases. However, not only the number of recipes are growing daily, but also the number of providers. It is therefore interesting to provide support just from the beginning, which is why we want to explore different versions of an existing algorithm using the example of recipe recommendation. There are several papers about recommender systems in the food area. Most of them focus on predicting similar items based on past user data. Even if those recommender systems are more famous, it is also important recommending good items when an application has just been released or a new user has just been registered. Knowledge-based recommender systems currently only get lower attention. The current state of the art is mainly about food recommender systems, including the health aspect, or general papers focusing on knowledge-based recommender systems. We therefore want to explore a knowledge-based model from an end-user perspective. We specifically examined the design of a knowledge-based model in a user-centered way and outline whether they could meet the end-user's needs. To get insight into the characteristics about why a different recipe is chosen by a user, we conducted an interview study with 11 people. The participants were between 22 and 65 years old and regularly cook. Based on the qualitative interviews, we were able to come up with a list of 27 different characteristics which are important while deciding for a recipe from end-user's perspective. To reach a higher sample, we added these characteristics to an online survey. In total, 272 participants rated their characteristics according to their importance to choose a recipe. The last step during our pre-study was to analyze the results. The displayed figure shows the collected characteristics according to their importance. The higher the rating, the more important the feature. As you can see, the top 5 characteristics are the occasion for cooking or searching a recipe, the available ingredients, the healthiness of the recipe, the expiration date of some ingredients, and the total time needed to cook the recipe. For our study, we used an open source database which was cleaned and extended using the 5 most important features discovered during the pre-study. Afterwards, we implemented 3 versions of a similarity metric. The simple similarity rates any deviation between 2 items as negative and weights every feature equally. Thus, it cannot be adapted by the user at all. The other 2 versions of the similarity metric can be individually adopted by just adding an individual weighting for different characteristics or by also defining accepted or maybe wanted deviations. In the course of the work, we want to investigate which expression of the metric is to be preferred in the field of recipe recommendation and whether it is preferable to a usual cosine similarity. To evaluate our metric, we set up a qualitative user study to see if there's a general preference towards one of the 3 versions and if the preferred one is also preferred over the cosine similarity. During our study, the users first had the option to adapt the weightings and the accepted deviations. These individual adaptations are taken in the second step to calculate 3 different alternatives for a random recipe, which are presented to the user and request to select the best one. After the 10th run, the preferred metric will be tested against the cosine similarity. Because of the possibility of having chosen 2 metrics equally often, the less complex variant will become the winner. This approach can be called winner-takes-it-all principle. In total, we interviewed 24 participants and thus got 24 winners and 240 recipe decisions in the first and the same amount in the second round. During each evaluation, it became obvious that the general importance of the characteristics is assessed differently than the importance of which characteristics should correspond with the searched alternative from an end-user perspective. For example, even if the ingredients are the most important characteristic for a dish, the importance that the ingredients are the same when searching an alternative is less important. This mismatch clearly shows that it's not necessarily the obvious criteria that lead users to favor or disfavor a proposed alternative. Therefore, it is always important for a designer of a recommender system to exploratively examine which criteria are the most appropriate, whereas qualitative user studies can be used mainly for the pre-selection of possible criteria. Comparing the results, the simple similarity can be outlined as winner in 54% of the cases. As this winner was identified with the winner-takes-it-all principle, a lot of information got lost, motivating us for also having a look at all decisions made by all users during the first part of the user evaluation. From 240 decisions, the recipe recommended by the simple and the asymmetric similarity were chosen nearly equally frequent. They differ by only 2%, which correspond to 6 decisions, which is why we are not able to outline one algorithm which is generally preferred. Based on the comments during the user evaluation, we can hypothesize that when looking for the most similar recipe, simple similarity was found to be the winner. But when a similar recipe should be different in some ways, weighted or asymmetric similarity was preferred. Due to the small sample, we were not able to check this hypothesis. Nevertheless, based on the second part of the user evaluation, we can conclude that each variant of the algorithm outperforms the cosine similarity. The second part of our evaluation was the calculation of the coverage level, which may provide data about whether all relevant elements can be displayed. Our interest was mainly whether and what kind of filter bubble exists. The coverage was calculated by letting each similarity calculation recommend the best 5 options for each recipe in the database. Afterward, the size of the filter bubble for each similarity calculation was checked by calculating the percentage of recommendable recipes. Because the recommendations from the weighted and asymmetric similarity change their recommendations according to the individual adoptions, the individual settings from the user evaluation were taken. This results in 4 different degrees of coverage, whereby the degree of the coverage of the weighted and asymmetric similarity depends on the user inputs and thus also differs greatly among each other, as shown in the example. The simple and cosine similarity coverages can be computed without any user input and therefore don't change. As displayed, the coverage of the 4 algorithms vary greatly. Of the 3 algorithm variants, simple similarity has the largest coverage, but also the largest blind spot. With increasing possibility adopting the similarity, the items that can always be recommended increase and those that can never be recommended, so the blind spot, decrease. Also the items which can only be recommended based on the user input increase, which let us think that the algorithm identifies items which the user would dislike. Including all recipe choices from the first part of the user evaluation, we can see that even though the coverage of the asymmetric similarity is the lowest, the alternative calculated by this metric was chosen almost as often as the alternative suggested by the simple similarity. Moreover, in the second part of the study, we found that the option recommended by the cosine similarity was the least selected but had the highest coverage. This suggests us that high coverage is not an indicator of a better recommending algorithm. To conclude, although we could not obtain clear results on which similarity metric should be preferred in general, we found that the recipe recommender system application domain, cosine similarity is not the best starting point. Moreover, we have shown that the three variants of the similarity metric have a higher risk of a small filter bubble, but this does not affect users not to select the recipe computed with this metric. This leads us to conclude that the largest filter bubble is not an indicator of a better metric. In addition, we were able to show that the perceived influence of a feature from the end user's perspective does not necessarily correspond to the actual influence. Although our study had some limitations and was focused on a specific application area, it contributes to a better understanding of knowledge-based recommender systems from the end-user perspective. We hope to inspire not only researchers in the field of recommender systems, but also designers in the field of new methods for designing explainable machine learning. That's all for today. Thank you for your interest in our work.